gonna come in a different costume tomorrow?
We'll see. I have to see what I can put together.
A more optimistic costume.
Are there like
Yeah.
2 testing locations and then? Oh, I'm actually taking the Untitled Chapter. Are you gonna be dressing up for the
Sorry.
Yes.
Oh, you don't want to see me? Ouch. 54-100 only. This is for people in 54-100. That's where I'm going to be tomorrow. Okay. So you guys might have heard we have a quiz tomorrow.
Really?
So we're going to do a review for that. Did everyone turn in PSET 6? Yes? Good. All right. So what's on this quiz? Numerics and graph stuff. So are there any specific pain points? I have problems prepared now, and then at 8 p.m. there's going to be a review session for concepts. So now problems, 8 p.m. concepts. Tomorrow Yafim has office hours at 5 p.m. Conveniently placed before the quiz, poor guy. So take advantage of that. So yeah.
Numerics. On PSET, we were mostly asked PSET 5 or whichever came before. We're mostly asking the running times and things like that. But the numeric lecture notes are kind of detailed and go into Newtonian methods and all that. How much detail do we need to know?
So on the PSET, we make your life easier by giving you the pseudocode of the code that you needed to implement. And we asked you one algorithm design question, that problem of finding the kth root. And that required you to understand almost everything that was going on. We'll want you to understand things that are going on to come up with something fairly similar to what you've seen. So yeah, I know that I told you guys before that ignore numerics, just close your eyes and pretend it didn't happen. Actually, it turns out there's a significant amount of numerics on the quiz. So we're going to start with a numerics problem and go through it. I'm really sorry about that. It's clearly, I didn't have my way for this, right? Okay, so we studied 2 big things in numeric. Karatsuba, which is really easy, compared to Newton, which requires a lot of understanding. So we're going to spend our time on Newton today. Okay, so anything aside from that? Yes?
The thing we were just talking about before you were here was what kind of edges are produced
Okay.
by depth first search versus breadth first search.
And why do they matter?
And why do they matter? Okay.
It's probably going to be a question.
So I'm going to go on this very quickly now because I want to cover problems. But tonight, this is on the outline for the review. So if you guys can make it tonight.
I can't make it.
Sorry. Well, they're also in the lecture notes, but I'll go through them very quickly now. Okay, anything else?
Making trees out of Dfs and Dfs, this might be tonight also.
Making trees.
Or your search trees. So, you know, instead of, you know what I mean by that?
Do you mean graph transformation?
So you've got a tree and you search through it. So then when you're searching through it, the result of searching it, you can put that into like almost a binary tree.
Okay, so how Bfs and Dfs work and how they produce trees, I'm assuming, right?
Yeah.
Because if you start out with a tree, everything's going to be really nice and simple.
Right.
Yes?
Bidirectional search.
Okay.
Is that going to be included?
At a very conceptual level, because we didn't give you a piece on it.
Wait,
Six.
what's not what Rubik's was?
Yeah.
It was
Sorry?
bidirectional.
Well, it's not going to be on it, so we're happy.
Well, I mean, we didn't give you, you kind of had to solve the problem just by, we had to tell you, this is bidirectional Bfs, go code it up. This is bidirectional Dijkstra, go code it up. So we're not going to ask you anything too fancy on them. So nothing past the PSET.
We had a question, like, when you were studying Dfs, saying that how there would be, like, levels of graphs.
Yep.
Could there be, like, a review about that?
So levels of graphs is in the levels in Bfs or the levels that we're using when we're building graphs?
copies of graphs and then
Transformation.
Yep, okay, transformations and layers. Yeah, I think this is important.
Maybe
So.
particular tips on what kind of transformations we might encounter.
And, like,
Sure, problem 1 has this transformation, problem 2.
Yeah.
basically, like, when do we use these? Like, is it when we are given more than, like,
It's when you
one
want to keep state.
parameter for cost? Or
So I have some problems on this, but we have to have a deal. You guys have to help me go through the problems fast enough so that we get here. Okay, so if you know the answer, say the answer. Don't let me wait. Okay.
Also, when you run Dijkstra and Bellman Ford on a graph with just positive edges, they produce the same shortest path weight, but might have different trees. So
Yes,
why is that?
that's conceivable. Because
It was
they...
one of the questions on spring 2011.
Okay, so first off, they both have positive edges, so they both work, right? If you had to choose, which one would you choose? If you had to choose, which one are you going to run? Which one would you run? Okay, why the extra?
Faster.
Faster. Okay, so positive edges. The extra is faster. Now, if we're going to run both of them, they relax edges in different orders, right? So let's say we have this. By the way, you guys remember the sequence of diamonds, right? My nice example that shows that the number of paths in a graph is exponential in the number of vertices. So let's have one diamond. 1, 1, 1, 1. S, A, B, T. So say we're looking for shortest path from S, right? So the distance from S to S is 0, and everything else starts out as infinity. SA is infinity, SB is infinity, ST is infinity. Suppose I relax edges in this order, 1, 2, 3, 4. What am I going to get? If I relax SA, then the distance from S to A is going to become 1, right? Because it's 0 plus 1, 1. And then the parent of A is going to be S. Now say I relax AT. The distance from S to T is going to be 2. Sorry. Parent of T is going to be A. Right? Okay, now I'm relaxing this one. This is going to become 1, and the parent of B is going to become S. And as I'm relaxing this one, nothing happens because I already had the distance of 2. Now if I relax them in this order instead, so the bottom ones first and the top ones afterwards, I'm going to get a different path, right? Okay, so what path do I have now from S to T?
Right now you have SAT.
Okay, why SAT? How do you compute the path? Parent pointers, right? Start at T, look at the parent pointer, look at the parent pointer. So because I relaxed them in this order, this path was considered before this path. So the parent pointer of T is A, but if I relax them in the other order, the parent pointer could be B. So by the way, this could happen if you're running Dijkstra or Bellman-Ford, or if you're running Dijkstra, it's just about how you're going to have the ties separated. So your priority queue implementation might give you different paths. Does it make sense now? So it's the order in which edges are relaxed. That's what defines which path you're going to end up with. Okay, hopefully useful. All right. I saw 4 hands before. Yeah.
Just overall, how similar is this test compared to like this test?
Less algorithm design, more concepts.
Oh.
Yes.
And, well, okay, not less algorithm. So it's not going to be as much out-of-the-box thinking. It's going to be a lot more of what we drilled already. So as a hint, what kind of problem did we practice over and over and over?
States.
Okay, graph transformation, right? So chances are you'll see that.
What's graph transformation?
You have multiple nodes for UPFS.
So we start with a complicated problem and we reduce it to a shortest path problem or to a shortest length path problem. Okay, cool. So that being said, let's go. Numerics, everyone's favorite topic. So suppose we're trying to compute this. Cube root of 6006. And the problem statement says this. You start out with an initial approximation of 1, and it wants 2 approximations after that. The problem also tells you which function we're going to use, but why don't we make this fun and try to guess what the function will be? Okay, x cubed minus 6006. Why did I choose this function? Well, not me. Why did you choose this function?
Because the word really.
Okay, so reason number 1. Right? Important. It has to be 0 at the answer because that's what Newton's method gives us. And what else?
Multiplication is easy, and the derivative is also multiplication. Like,
Okay. So it's easy to compute whatever Newton's method wants us to compute. What does Newton's method want us to compute? So given an approximation xi, how do we get to the next approximation, xi plus 1? Formula. By the way, this formula should be on your cheat sheets. If it's not, no sympathy for you.
it's like, I don't remember. Xi like plus f over f prime.
I don't remember.
F
Where's
prime
the
to the bottom.
prime?
F prime to the bottom.
So yeah, where's the prime? And is this right?
Isn't it minus?
Isn't it minus?
Maybe.
Sorry.
So yeah, if you guys start out with the wrong formula, you'd get the wrong answer. Again, no sympathy. So get that on your sheets. Okay, so this is what we need to compute, right? You start with an approximation and you have to subtract this. So this has to be easy to compute. What if I chose instead a very nice function, x minus. This is clearly 0 where I want it to be, right?
But we don't know what 6.
But if I'm trying to compute the successive approximations, very good, I'm getting what? F of x over f prime of x is x minus square root 3 666 over, what's the derivative of this? 1. So I haven't done anything, right? In order to compute the successive approximation, I have to know this number. So this doesn't get me anywhere. That's why it's a bad function. By the way, it's not enough that this is easy to compute. What you want is this guy has to be easy to compute. In the case of division, we had a function that looked pretty wacky, but then when we divided that by the derivative, we got something reasonably nice. So this has to be easy to compute.
So we changed it from that form to this form just because this one is easy to compute? Or
So we're using this one because this one, let's see how easy this one is to compute. Computing this one requires that you know the answer to your original problem, which is not cool, right? So you're trying to compute this number. But if you use this, Newton's approximation requires that you compute this. So you have to do this, which is what you're trying to do in the first place.
no, wait, like I'm confused. We went from x cubed minus 666 to x minus cube root of 666. So like,
So this is a good function. We can use this. This is a bad function, and I was asking why is this a bad function?
Oh, okay. Okay.
Okay. So let's see. If we try to compute it using this, what do we get? Xi minus
X cubed minus 6
6 divided by
3x.
Okay. So someone simplify this for me?
Xi minus x over 3 plus 706, 606 over 3x squared. Oh, well, it's been divided for at least 2,000.
I'll choose the easy step. Okay. So what's x1?
You plug in x0.
Okay. I heard it 2002. I don't think it's
2002
It's very close.
and 2/3, 0.67.
okay. Cool. So 0.67. Let's get to that later. I don't like fractional numbers. I mean, this is the right answer math-wise, but we'll get to that because if we want to code this up, we probably don't want fractional numbers. So very good point there. What if I want to compute x2? I take this guy and I plug it into where? This thing over here, right? So this way I can compute approximations that get closer and closer to my original value. Okay, does this ring a bell? Yes, everyone's happy with this? Cool. So how about the initial guess? Here we started with a known initial guess. Is this a good guess?
It's a really bad guess. 2002?
No, I mean 1.
It's also a really bad guess.
What would you guess?
11 and a half.
All right. So you're saying 11 and a half would be a nice guess.
Do it.
So first off, let's see, what does Newton's algorithm guarantee? What, if the guess is really, really bad, would we get an answer all the time? Maybe it takes forever, but we'll get an answer. True or false?
True.
You always get an answer.
Not true, sorry.
Well, it depends on how accurate you want your answer to be.
Okay, so what does Newton's method guarantee?
1 minus error has to be less than.
Yep.
something like
So
that.
what's the fancy math name for that?
Quadratic convergence or something?
Quadratic convergence. All right. So this is what Newton guarantees. Quadratic.
How many converges then?
So what does this mean? For all your approximations, they're all going to be xi. If we write them as true answer times 1 plus error I, so this error is the relative error of the approximation. Newton's method guarantees that the error at each step is squared. So if this guy, if E0 is greater than 1,
Oh,
would we get an
that's,
answer?
No.
Okay, so what do we need? What's the minimum that we need? E0 has to be between what and what?
Negative 1, 1 or 0?
We need 0 and 1, right? Because 1 would be less than 1.
Negative one.
Negative 1.
People take this.
Oh, absolute value.
I think if you score negative, something smaller than negative 1, you'll get a positive and then. So let's say this works. So then x0 has to be between what and what in relation to the real answer.
X the real answer minus x0 over
So between
X plus
2
1.
times the actual answer and 0.
Okay, so this is a sucky guess. We can do a lot better, but at least it will make the thing converge. Fair enough? Okay, now what if I want a good guess? First off, let's backtrack to a more general problem because this is easy, right? You plug it into your calculator and you have the answer. So what if I'm trying to compute cube root of r? Can everyone see, by the way?
Yes.
Okay, so I'm trying to compute cube root of r. R is a number. Suppose I'm trying to compute, for example, cube root of 2. What's the first thing I need to do? I'm going to code this up, by the way. Well, not me, but suppose we want to code this up. What's the first thing we want to do?
I think you want an initial guess and a function.
Okay, so we're going to need an initial guess. That's good. And what else do we want?
You decide how much precision you want, right?
Yep. And why is that?
Because this cube root of 2 is 1 if you round down. And that doesn't tell us very much. I mean, I don't know, we don't like fractions.
We don't like fractions. Okay, why don't we like fractions? It's a lot easier to code.
Decimal point then.
Yep, you have to deal with decimal point, and we don't like that. So we want to take this problem, and we want to move it into integer land. So what we did here has fractions. We don't like that because that's a pain to code. We didn't make you code fractions on the pset, right? So then we'd better know how to avoid fractions if we want to solve real-life problems. So we're going to say that we're happy with some amount of precision in the answer. And then we're going to do something that lets us do all our computations in integer land. because that's a happy place. So how do I, suppose I want, suppose I'm working in base B and I want D digits of precision. What do I want to compute? How do I transform the problem in that way? Yes?
You multiply root 3, I mean, 2 root 3 times b to the d.
Okay, so we want the answer to be 2 times b to the d. And if we're integer land, what are we actually going to get? So suppose b is 10, let's work with familiar numbers, and d is 2. So we're going to want to compute square root of 2 times 100. Does anyone have a calculator and can tell me what square root of 3? First few digits?
Cube root of 2.
Sorry, cube root of 2. 1.2. So let's say that square root of 3 is 1.2345. Hopefully someone will fix this up for us. But let's say it's this. If I multiply it by 100, what will I get? 1, 2, 3 times 4, 5. So multiply by 100 means you move the decimal point to the right. Right, so it's still not an integer. If we work in integer land, our algorithm will return an integer. What's the integer that we're hoping our algorithm will return?
123, right?
We're hoping so, right? Why? What can you do with 123? Shift right. So if you divide this by 100, you get 1.23, and this is our answer with 2 digits of precision.
Do you want the actual? It's 2599.
That's pretty close.
You guys are good. Okay. So our algorithm will give us this, right? So it's not going to give us exactly cube root of 3, cube root of 2 times 100. It's not going to give us exactly this value. What's it going to give us?
2 digits close to that.
So it's going to give us an integer, right? So what kind of integer? Math.
Truncated?
Okay, what's the math for that?
Floor.
Truncated, floor.
Oh.
Very good. So this is what we're actually going to compute. Actually, because we're in integer land, we're going to have floors at every step when we're doing that approximation. And there's a fancy proof for Newton that says that even though you're taking floors all the time, it will still converge to the right thing. So in order to compute this, how are we going to transform the problem?
Slide the BD into the
This.
pattern.
Okay.
We gotta put a 3 in there. B to the 3D.
So we're actually going to compute cube root of 2 times b to the 3d. Fair enough? And if we slide this right by the digits afterwards, we're going to get our 2 digits of precision. Okay. So now I figured out my precision. I want an initial guess, and actually I lied. There's one more problem. Running time. Do you guys want to start with the running time or with the initial guess?
Yeah.
Okay, so what do I want from a good initial guess?
Between 0 and 2x.
Okay, so if I don't have that, the algorithm will crash and burn. When we did Newton in Recitation, I said that I would like 2 things. And I backed that up, I coded that into Pset 5 when I did the guess. So what are the 2 things that I want from a good initial guess?
Order of magnitude.
Okay. Perfect. Okay, so order of magnitude is a fancy CSE way to say right number of digits. Suppose we're computing this, or suppose we're computing the cube root of some number in base b. So suppose suppose r is somewhere between 0 and b. It's one digit in base b. How many digits is this result going to have?
The amount of digits divided by 3. The amount of digits in 2 times b to the 3d. Which
Okay.
is whatever b to the 3d is.
D plus 1.
Okay, so roughly either d or d plus 1. Say d plus 1. So a decent approximation would be 1 followed by d zeros. An even better approximation is what if we can get the first digit right or almost right? How would we do that?
Pick off the first digit of our r.
Okay, and I promise that r is one digit. So let's say we pick up r and
We'll do Newton's method on that. I think we just guess 1. Is that fair?
So you have to take the cube root of it. So
You
you
could
need
use
to
some kind of inefficient.
yeah, what's some kind of inefficient way that we can think of quickly?
Can you...
Binary search.
Did you say
yeah.
divide and?
Divided by 2r. Or,
Oh, sorry, I thought you were going to say divide and conquer. So I heard binary search, so binary search wins. So we're going to do binary search. Binary search from 0 to r. Right, in order to do binary search, suppose I have my guess g. I want to see how g compares to cube root of r. How do I do this? So this is equivalent to g cubed compared to r. G cubed is 2 multiplications, so I know how to do that. Okay? Make sense for everyone? Sorry. R. My bad. So this is going to be one digit in base B, so hopefully not too much work. Okay. But remember this, you can't do the comparison directly because you can't compute this directly, so you need to do it this way.
So R is just the first digit of the number? You're
Yep.
computing
So we're going for an easy, slightly easier problem where we're trying to compute the cube root of a single digit number to an arbitrary precision. You can make it harder, but there's no point right now, so we'll stick to this. So how much time will this take? How many approximations will I need to do? By the way, so suppose I compute my approximations, right? So I compute x0, x1, x2, x3, so on and so forth. When do I stop?
Both the digits are the same.
All the digits are the same, so
Or when the
so when one approximation is the same with the next one.
from the next.
That's what you're,
Yeah.
right? So these are all integers. The moment I get to identical integers, I know there's no point to continue because I'm going to get the same value forever. Also, this means that Newton's method has converged on this integer, so hopefully I will get the right answer, which I can convert into the right answer. Okay, so how fast does this work? What is n? When am I going to stop?
log base 2 of d.
Okay. So n is so the number of digits in my approximation, the number of correct digits doubles every time. So after log these steps, I have the right answer. Now what if instead of doing this, I did binary search? So instead of doing Newton's method, I do binary search on 0 to r. I can do that, right? Because I can get a guess, and then I can use this to see if my guess is right or wrong. So in theory, I could do it in binary search. How fast would that be?
what is the difference between big R and little r?
Big R is, oh, I didn't write the big R. Big R is this guy here,
Oh, okay.
and this is little r. Sorry. Good question. Apologize for that. So r is little r times b to the 3d.
D times log 2b.
To the D.
Log R.
Log to the D. Oh, it's the same thing, right?
Yeah. I don't know why I did that.
Okay, so the number of guesses is
Log big R.
log big R, and then someone was one step ahead and said it's order of D times log little r. Or I think it's D plus little r. So this is order of D. Does this make sense for everyone?
I didn't quite follow what happened there.
So I'm doing a binary search on the range from 0 to r. How many steps? How many guesses? Log r, right? This is binary search. R is little r times b to the 3d. So if we log this, log r is log little r plus 3d log b. B is order 1, so we get order of log b. Okay, so Newton's method is exponentially faster in terms of the number of digits compared to binary search. So if you can pull it off with Newton's method and you have big numbers, you probably want to use Newton's method, because binary search will give you a slower algorithm. Okay, how are we doing with these concepts? I see everyone's unhappy. Is it because of Newton or something I
Can
said?
you summarize the difference, why you're doing the difference between binary search and doing Newton's again? So you said binary search takes how long versus Newton's method?
Okay, so how do you do binary search?
Divide and conquer, which is
Divide and conquer, right? You start out with an interval. You guess somewhere in half, and then you see which half of the interval you correspond to. And your interval will half in size every time. So given the initial size of the interval, the number of guesses you have is log of that interval size. In this case, we're guessing a number between 0 and r. So the big goal is to compute cube root of r. And we're guessing that, hey, it has to be somewhere between 0 and r. So we're going to do binary search on this. And in order to see how our guess compares, we're going to use this trick here. So the number of guesses we make is log r. Now r is that number over there. It's little r times b to the 3d. So how many digits does it have? Roughly d digits. So log of r is going to be order d. Okay, so if you do binary search to guess a d-digit number, the running time will be roughly order d, order of the number of digits. If you use Newton's method, and your function is good and everything converges, then you have quadratic convergence, which guarantees that you'll have log of the guesses, log of the approximations. So Newton's method is a lot faster for big numbers, because you have a log there instead of d. So this is the big difference between them. But for Newton, you need a lot of things, right? You need that function, you need an initial guess, you need a lot of things to make it work. Yes?
So is that just like the number of times it runs? Because don't you have like a multiplication and a division?
Yep, so this is the number of guesses.
Okay.
The total running time is quite different. You need to jump through a few more hoops to analyze that. But this is the number of guesses or approximations that each method makes. So if your math would be order 1, this would be the running time. If the math isn't order 1, then it gets more complicated.
So like, what's the running time of a division?
What's the running time of a division? Using Newton's method? It's the same as the running time of the multiplication that you're using to compute your approximations. And it's like 2 pages of notes prove that, so let's not go over that now. But the idea is that every time you're multiplying, you start multiplying small numbers, and the numbers double in size when you're multiplying them. So only the last multiplication counts. All the others are tiny compared to that. Okay. Anything else about Newton? Sorry guys, we have Newton on the exam, so we have to go through this. Let's go through some fun graph problems. Okay, so we kicked off these two, graph BFS edges and graph transformations. Okay, I'm going to do a graph transformation first because I think that's more useful than BFS edges, but hopefully I'm going to get to both. So suppose I have a graph. Each path is either red or blue. By the way, no political connection whatsoever. And you have weights on each path. So we want a path from S to T with the following constraint. So these weights are the cost of maybe how much gas you're spending to go on that road. So in order to switch from a red edge to a blue edge, you also have to pay some money. You have to pay a cost of 5. So if you're gonna go from S to A, let's call this guy A. If you're gonna go this way, then your total cost is 314. If you're going to go from S to B, then if you go this way, your total cost is going to be 3 plus 1 plus 5 for switching from a red to a blue edge. So the cost for switching from red to blue is 5. The cost for switching from blue to red is 5. And I'll let you guys think of it for a bit while I erase the board.
What's your goal with finding the best path from?
Best path from S to T, smallest total cost.
Okay.
So any thoughts? Yes.
This is kind of like on the run, but Karatsuba will connect all the red nodes, or the red paths, and create another one connecting all the blue paths, and then try to find the shortest length to T using just using those two graphs, I guess.
So you're going to create a supernode connecting path. So how does this work?
So I guess you create you create the path from S to T just using the reds.
Okay, so I'm going to copy everything and use the reds. So S, C, B, T, A, and I'm only going to use the reds. So red, 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 red. Okay.
And then, wait, is that all the red paths? Oh.
I hope so.
Alright, and then you're gonna try doing that with the blue paths as well.
So, am I creating another copy of this?
Yeah.
Okay. Let's see what else. Okay.
From S to T, right?
Path from S to T?
Yeah, so you just compare, well, this is one way I go. You compare the path from S to the path from T. So you completely take that out, the additional cost out of the equation, just by comparing those two and seeing which one is the shortest path. And then
It's correct for this graph, but it's
it
not
wouldn't be
correct.
correct for geometry, I guess.
It doesn't illustrate the trade-offs between.
And the last option would be combining
Okay, so if I do this so far, so I've taken the original graph and I created 2 copies. One that has all the red paths, one that has all the blue paths. By the way, let's label this, the nodes are,
So it would work in
And
this
blue.
specific case because you break the guy immediately.
so if you compute the 2 shortest paths here, you'll get the path using only reds, path using only blues. But you're not expressing the fact that you're allowed to alternate between reds and blues. How do you express that?
Make a lot of control corrections.
2 layers. Okay, so these are 2 layers. This is the red layer, and this is the blue layer. And how do I connect them?
If there's an edge connecting them on the upper graph, then just connecting them.
Or connect the respective nodes and add 5, make it a 5.
Okay, both answers work. They have the same number of edges. The last answer is easier to visualize, so I'm going to go with that. So I can go from the red world to the blue world and back if I'm willing to pay 5. So this is what
And then you just use DFS with the new, I guess, edges. Or not DFS, but Dijkstra's.
all right, so all the edges here are positive, right? So I'm going to use Dijkstra.
Is there any case in a positive graph that Dijkstra is slower than Billingford? Because one's like V log V and the other one's like VE, right? So if you have a lot of
Okay, so what's Dijkstra?
V log V,
Almost.
maybe.
It's E log V, I think, right? But that's the theoretical best case ever. High constant.
So
value.
actually the theoretical is E plus.
Yeah, that's what I meant. Yeah.
Oh.
This is what you'll get with heaps. So this is what we got in the P set.
We don't have to know like the Fibonacci heaps.
What was the first one?
First one's like Fibonacci heaps,
Yeah, and the second
and
one's
it's got a really high constant factor, so you never actually use it.
So this is a nice theoretical thing, and this is what you get in practice if you use regular binary heaps. And so you compare this to Bell and Ford, which is, whoops, V times E. I'm gonna guess that this is faster no matter what.
Yes. Okay.
Okay.
So the theoretical one could be slower than possibly. The Fibonacci one,
It could be the same.
because
So-
if you have a ton of vertices without many edges,
Okay, if you have a ton of vertices but not too many edges,
yeah.
then you're saying that this is gonna be bigger than. So what do you do in that case?
I mean, you could just ignore the vertices, I guess.
Okay, so if you have a ton of vertices and not that many edges, so if you have edges smaller, edges smaller than vertices, then some vertices have to be unconnected.
Mm-hmm.
So what do?
You just ignore them.
You're not gonna reach them anyway.
How do you
right?
ignore them? How do you ignore them in?
Oh, I see your point. So you're never gonna get to them anyways. So.
Well, no, but once you started at one, you're gonna have to touch all
Well,
of
okay.
them.
Well then. Oh.
They're all gonna be in the heap. Or, yeah.
No, don't put them in the heap until you look at them.
Well, there's a starting. No. There's a starting point, right?
Let's see if they're
If you
adjacent
can't go
to
anywhere
each
in the starting point, you're done.
Okay, so you take the starting point and you do.
Check its
Yeah.
adjacency.
This super
Okay.
awesome Dijkstra.
So I would take the starting point and do a BFS and ignore everything else, and that is clearly order of how many vertices and edges you have reachable from that. So that will give you a nice graph. Either that, or if you initialize your Dijkstra carefully enough, this actually only reflects the reachable edges and vertices. So you'll never have this. So either one works. In theory mode, it might be better to say I do a BFS and reduce the graph, because that's easier to argue. Yes.
So for this, so the fact that when you make, after all, like, are we going to be asked, I guess in general my question is, are you going to be asked, like, to running times for different transformations, or like using different algorithms?
Well, so at the very least, like last time we said,
So like,
this is the problem. Give us an algorithm with this running time.
Right.
So you have to be able to know your transformations. So not the running time for computing the transformation, but you have to be able to know how much bigger the graph gets and what that implies for the running time. Turns out that usually for these transformations, you can compute them in linear time. So the time for computing a transformation is much smaller than the time for running Dijkstra or Bell-Ford. So that's why we don't really go into that. This one's definitely linear time. So what happens to this? What happens to the graph in this case? Number of edges and number of vertices.
The number of edges increases by v, and the number of vertices lowers by v.
So you plug this into Bellman-Ford or Dijkstra, you find out the new running time. So every time you see what's the size of your new graph, and you plug that into the algorithm. Okay, so what's the intuition behind this? Did everyone get this problem? So it's the old problem that we're going through again and again, where you have a graph that's 2D, and we want to compute something that Dijkstra can't compute on its own, or that Bellman-Ford can't compute on its own. So in order to be able to compute those things, we need to add additional state to the graph. And the way we do that is we make copies of the graph that we call layers, because we're thinking that if you take that 2D map and you create copies of it, you basically have a 3D graph where each layer is the original graph. And then that's the science part of the problem. The art part of solving the problem is figuring out what those layers are and how you connect them. Because by doing that, you can solve a ton of problems, as we have seen in this class.
Is there a possibility that you would have a very large number of layers if you had to do like permutations of, you had like different choices to make instead of just a red or a blue?
Yep. So is there a problem where we had a ton of layers?
Mm-hmm.
Yep. Okay, so 2 problems, right?
One for every
So-
second.
So these are the layers, presumably. We had 2 problems that had a ton of layers. One of them was the highway problem, where you had timetables. And there the number of layers was the number of minutes in the day you're considering, so roughly 1400. And the other one was StarCraft, where the number of layers was something ginormous, right? So as long as that fits the theory, that's fine. As long as the number of layers fits whatever the problem wants you to compute, it's okay.
So is computing another layer, is like transforming or making another layer, is that like in the v time because copying the number of vertices?
Yeah, so you should be able to implement this in order of b plus e, which is what you need to output the new graph description. I claim that for this you can't.
So for E5, I guess, how do you get that?
So for each vertex, you're going to create a red copy and a blue copy.
Right.
2v. This is easy. Now, the red edges stay in here. The blue edges stay in here. So nothing changed so far. But each red vertex needs to be connected to the blue vertex by an edge of weight 5. So that means that we're going to copy over the original edges, and we're going to add v edges that connect the vertices.
Oh, to each other.
Yeah. So we're not going to ask it about the running time of the transformations in general, because we assume that they can be done in linear time. But you need to at least have a sense of whether your graph is going to double, whether it's going to increase exponentially, or what's going to happen to it. So let's make a small tweak to this problem. Suppose that instead of having this, I can go from red to blue, but once I've gone from red to blue, I can't go back. So I can start out either red or blue. I can go red to blue, but once I'm in blue, I can't go back to red.
Make those directed edges.
From where to where?
The red to blue.
Okay, so this is how I express constraints in constraints among layers. Before we had 2 layers, red and blue, and we connected them by an edge of weight 5, which says you can go from red world to blue world and back. All you have to do is pay 5. If we have directed edges, then this is a constraint. If the constraint said there's no cost, but you can only go from red to blue, you'd still have to do 2 layers and keep track of which layer you're in. But then your edge would be weight 0. Since we have to pay, the edge is weight 5. So we can use layers to express additional costs or just to express constraints. Does this make sense?
Would this include also like back edges or forward edges as well?
Let's get to that. Okay, so does this make sense so far? One more question. What shortest path do I want to compute here? To make sure that you guys got it.
Oh, you have to do 2 of them, maybe 4 of them.
Okay, I like 4 of them. So I have to do SR, TR, SR, TB, SB, TR, SB, TB. Fortunately, our algorithms give us the shortest path from one source to all the other vertices, so I'd only have to run Dijkstra or Abel and Ford twice. What if I want to run the algorithm once? What do I do?
Vertices on the edges.
Okay, so supernode as a source, supernode as a destination, and I connect them to what?
Zero weight. Zero weight the other side.
To
The two SRs.
okay, very good. And
Zero weight.
so what happened here? This says you can go anywhere, and this says you can come back from anywhere.
Bridge between the worlds.
Yep.
Yep.
So do we want these to be directed or undirected, by the way? Does it matter?
Directed. You can only go one way.
Oh, it depends on which problem you're talking about.
You don't want to.
I think if they're undirected, it shouldn't matter too much because there shouldn't be a path where you go back to the source and then you switch. But this would be, if you're on a quiz and you don't want to think about that, I'd make them directed just to be on the safe side.
So what were the 4 shortest paths you said you needed to calculate for the original problem before you added the supernode?
So we don't know whether we start out with a red edge,
Right.
with a blue edge. We don't know whether we end up with an red edge
So
or a
it's
blue
like
edge.
from, okay, so like from stay in red world, stay in blue world, red to blue and blue to red.
Yeah. Okay, cool. So let's talk about BFS and DFS very briefly, I guess. So BFS and DFS. What does BFS give us? Why is it useful? Shortest path in terms of number of edges, right? No weights on the edges. So shortest path using the number of edges. What does DFS give us?
Helps topological, yeah.
Hey man, you had this on the P set. I wouldn't call it nothing. Okay, how does BFS look at the graph? How does it partition the graph? Nodes are grouped into levels. So you start with a source, and then all the nodes that are 1 edge away are at level 1. All the nodes that are 2 edges away are level 2, so on and so forth. What does DFS give us? A mess, right? So it gives us edge types, and it gives us exit times. Exit times are useful for topological sort, right? Yes.
Also gives us a tree.
Okay, does BFS give us a tree?
Yes. Yes, they both give us trees.
So both of them will give us trees.
Awesome.
So what are those trees? For each node, BFS discovered it, or DFS discovered that node by going from some parent node across an edge. So that edge belongs to the BFS or to the DFS tree. How do we compute those trees?
Just do it.
So how do you, in BFS and DFS, what do you compute
to
to
adjacencies or something?
parent pointers?
Yeah.
So that's what you use to keep track of them. Sorry, the question is bad, but that's what I wanted to get out of it. Parent pointers. So DFS and BFS will both compute trees of the graph. Are they the same trees or different trees?
Different trees.
Probably
Different trees, right? Let's take this. S, A, B, right? BFS will give us this, DFS will give us this. Okay, what edge types do we have in DFS?
4 edges.
Okay, 4. Cool. What are they?
Those are just from parents to children that are newly visited.
Okay.
So I don't know how else to put it.
Okay, so you should have this on your cheat sheet, right? If nobody knows the answer, you should have it on your cheat sheet. So 3 edges, the ones that show up in the Dfs tree, backward edges, cross edges,
forward edges.
and forward edges. If your graph is undirected, what types of edges do you not have?
Forward edges. Forward edges and backward edges. Or no, forward edges.
Okay. So this is in lecture notes, and we're going to go over them tonight. But if you can't make it, they're in lecture notes. So you should have this on your cheat sheet if you don't know them. Right? Nobody answered today, so if you guys don't have them on your cheat sheet, I will be upset. Okay. Cool. More questions?
Or do those not exist in BFS? Edge types?
BFS uses, so out of BFS we get levels, and out of DFS we get those edge types.
Is there
A reason?
care about the edge types?
Some algorithms use them in their proofs. So the proof for topological sort uses the fact that in directed acyclic graphs you won't have some types of edges, and for the other types of edges it argues that the order that you get from topological sort is the right order. So it's mostly theoretical, but since we taught you about edge types, we might ask you about them. Yes?
So does DFS actually, like, is it able to distinguish between back, cross, and forward, or is it only like, does it only see that the node's already been visited or something?
So how do you make it distinguish between them? You have to, right? Because otherwise, why are we studying them? There has to be a way to distinguish between them.
Because DFS does recursive calls, you know when you do a back edge.
So let's do a DFS tree quickly. So suppose we went like this, and then like this, and then this. Sorry, I'm trying really hard to make up an example on the spot such that I won't just kill myself. How do I get that in?
Maybe an edge from the second one to the last one on the right.
Here?
Yeah, and like this will be the arrowhead, and we can start from the second one.
This one?
Yeah. Wouldn't that be a forward edge?
Okay.
Because it's like
Yeah, I like that.
downward, right?
Okay, I like that. Okay, so S, A, B, C, D, E. So assume this is the order that they listed in adjacency lists. So let's label all the edges. S, A, and S, B are what?
Forward edges.
Okay. AC, CD,
Forward.
CE.
Forward.
Okay. AE.
Where did those tree
Those are
edges?
true edges, not the forward edge.
That took a while, guys. That took a while.
But it goes forward.
Well, no, forward means like you're skipping a generation.
Okay, so the three edges.
Grammar comes in with it.
So the three edges are the ones that DFS uses to go forward. So they're the ones that map to DFS calls.
To traverse. I think the better one.
So how do we express that? So suppose you're at some node U and you have an edge UV.
The parent of B is U.
So you're at U right now. Okay, so V dot parent has to be U. And V is it visited or not?
Any vertex?
No.
So V is not visited yet. So this is a tree edge. Now let's compare this to a forward edge. So what happens to a forward edge?
Parent and children?
Parent ancestors.
Parent, yeah.
So you're at U right now. And you're looking at the edge UV. Right? So you're looking at the edge UV. UV would point downwards in the tree. What's true about?
V dot parent is U.
Okay.
Although you
So
can-
V dot parent is U.
V dot-
So
could
it can be the parent or the grandparent, or so U has to be somewhere up the tree, right?
Okay.
So I can have a ton of dot parents here.
There has to be more than one dot parent, right? Because otherwise it'd be a tree edge. It can't just be one parent.
Okay.
So you have to like recurse up more than once.
Yep. So for node you go up until you find U, and if you found U, then it's a tree edge. If not, sorry, it's a forward edge. Otherwise, if you find the root of the tree and you give up.
Then it's a cross edge. Right? If you go up and you go to the root, but
Yeah. So if you go to the root, if you got to the root, it's not the forward edge. Right now we're looking at what does it mean.
Oh, okay.
So U has to be somewhere on the ancestor chain of U. So if you keep following V's parents, you have to see U. If not, it's not the forward edge. Okay. And when you see it, did you visit it or did you not visit it?
Already visited.
Okay. So now we have two more edge types. We have back edges and we have cross edges, right? Show me a back edge here. DA is a back edge. Okay, back edges are also reasonably easy, so let's do those. What's a back edge? So I'm at U now. I'm looking at the edge UV.
Node to ancestor.
Sorry?
There's a node to an ancestor.
Okay, so who is whose ancestor?
A is D's ancestor.
V is U's ancestor.
Or
Okay.
well, yeah.
So if I keep going, U dot parent many times over, I should eventually see V. Oh, yeah. So the difference between this and this is whose parent?
Wouldn't U be a parent of V? Because we'll go from A to C to D, and then at D I realize that I can go to A, but I won't go because it's already visited.
Wait,
What?
so
We're just doing it.
So A is an ancestor of D because by the time I got to D, I've already set the parent pointers for C and D.
Yes, but wait. U dot parent is V, and U is A here, and V is D here. Right?
So I'm
okay,
at
got it.
U right now, so
Okay.
I'm at D, and
Okay.
I'm looking at the edge
Yeah,
UV.
makes sense.
Do we have a cross edge?
Do we have a cross edge in here? Good question. What's the cross edge?
Doesn't have
C.
Oh, yeah.
Okay, so this guy is a cross edge. So what's the difference between a cross edge and a forward edge?
Or it is visited.
It's not an ancestor.
The ancestor goes up to S.
So a cross edge is very close to a forward edge, except U is not an ancestor of V. V in the Dfs tree.
So
Okay?
basically, another way to say that is just they can do different subtrees. For the
Yep.
most part, that would work, right?
Yep. So the only common ancestor between B and C is the source. Okay, so please get these conditions in the notes. So as a summary, if it's an edge that DFS uses, it's a tree edge. If it's going against the way of the DFS, it's a back edge. If it fast forwards in DFS, so instead of going one level down, it goes multiple levels down, then it's a forward edge. And otherwise, it's a weird edge, so it's a cross edge. One way to look at it. Yeah.
Is this only true because we were going alphabetically?
Yeah, this depends on the order in which the nodes are listed in the adjacency list.
So it could have been like pretty different if
Yep.
we went from A to E.
Oh, yeah.
Okay.
Yep.
Sorry, I'm changing the topic a little bit.
you
Was this graph transformation?
Yeah.
Did you say that's moderate to like an easy example for transformation of test or issue item?
This is on the easy side. So look at the problems that we had so far. There are more problems in this review packet. There are like 6, 7, 8 problems. It's gonna be online. So it's the notes for this recitation. Sorry, bad name. So the notes for this recitation. This is on the easy side. The StarCraft problem last time is on the insanely difficult side, so that's not gonna happen.
I still don't even get that. Like,
That's on the hard
What do we
side.
conclude was the best strategy?
Sorry?
Do we conclude that there was a best strategy for StarCraft?
What was the answer?
So there's a, so we had a lot of simplifying assumptions, but there is a best order for StarCraft, a best build order in the beginning, right? At least until like 14 control points, there's a known best order for each race.
Are we gonna be asked like